Good morning. This session is titled Energy Innovation in Biomass. My name is Julie Kies. I work here with the state of Montana with the Department of Natural Resources and Conservation. I know a lot of you in the audience here, and there's some new faces as well. So we'll just have some cozy discussion. We had intended to probably hold off questions till the end with all the panelists, but I would say feel free to ask some questions as we go as well. It's my pleasure to moderate this. This session is billed as talking about biomass feedstocks from A to W, but I imagine there's some X, Y, Z too. But we called out algae, agriculture, forest, fungi, and waste, so we'll just touch on those a little bit and maybe some others in the mix. These are often lumped together as biofuels in kind of one category. And yes, they're all organic bio-based materials, but each have very different characteristics, they're different materials, they have different product pathways, different roles and opportunities, different end products. So I think we're going to learn a little bit about that today. And so hopefully what you take away from this is a broader view of that world of bio-based materials, mainly in energy and fuels and other co-products. And a picture of some of the realized and future potential of different biomass feedstocks. And then, of course, the social, economic, and environmental considerations for all of those. So the format today, what we're going to do, I'm going to introduce the panelists here, and then we're going to start with a brief presentation from each panelist, and then we'll provide some good time for Q&A with all three of them. We'll bring them up. So I'm going to just introduce all three now briefly. I'll point them out in the audience. We have with us Dr. Thomas Buchholz, who's visiting us from Seattle. He's a senior scientist with the Spatial Informatics group. He leads the forest and agricultural team there. Dr. Buchholz is lead author on a number of publications and reports on forest economics and forest bioenergy. We also have joining us Dr. Michael Wolcott. Dr. Wolcott is based at Washington State University. He is in the Department of Civil and Environmental Engineering, and he is co-project director of the Northwest Advanced Renewables Alliance, where he and I have intersected in some work here in Western Montana. We've enjoyed that relationship. He'll probably explain more about what that project is, so I won't go into it. And then we're going to start off here with Dr. Brent Peyton. Dr. Peyton is based out of Montana State University in Bozeman. He's with the Department of Chemical and Biological Engineering, is the director of Thermal Biology Institute, and is doing a lot of really interesting work that is outside of things that I know about, kind of at a smaller scale of microbiology, but I'm interested to learn more. So we'll start with Dr. Peyton.
All right, thank you. Thank you very much. So I want to thank the organizers for inviting us and setting this session up. The way that we're going to do this is start kind of at the fundamental research and work our way up this session. And so what I want to tell you about is some of the areas of research that have some promise. And I like to think about, just about everybody in the room probably has a cell phone. And probably everybody in this room can remember back when cell phones were mobile phones and they came with boxes and you had, carried a big box phone around. And then you can remember back when there were no mobile phones. And we're sort of in that stage of development right now where we're looking at the possibilities, looking at what you can do with biotechnology for fuels and renewable chemicals. Now, some of the current things haven't proved to be as energy efficient or as economically viable, especially with the cost of fuels, the low cost of fuels right now. But I want you to keep in mind that these things have lots of room for development. This is a small piece of the Montana State Energy Research Institute. We do a lot of work. We're about 10% of the research in the fungal and algal biofuel section, so that's what I'll be talking to you about today. So one of the things with, I'm going to start with algal biofuels and not go into, I could do an hour talk on the data on this, but what I want to do is present some concepts and then open it up for questions, obviously. Algae can yield more oil per acre than soybeans or corn than any known energy crop that we have today. Basically, you can get this from low-value land. You grow these in ponds, and so you can, anywhere you've got some water, and it doesn't even have to be good quality water. It can be water from coal bed methane, it can be seawater, it can be just about anything. You can grow algae as long as you have sunshine and some kind of water. You can grow these organisms in reactors like this, but when in the final version of this, they're going to be, think of algae ponds that are on the order of a square mile. So like you have a section of corn, you have a section of algal bioponds. The algae can produce biodiesel, that's the main fuel component, but they also can make carbohydrates, organic acids, some high-value products like omega-3 fatty acids, which these would be, they're usually, maybe a lot of people in the room take fish oil for their heart. That is, the fish oil is actually a misnomer. It's actually algae oil. The fish are just very good at harvesting the algae in the ocean, and the fish are much easier to harvest than algae are. And so they swim around, eat algae, accumulate the omega-3s from them, and then we harvest the fish. For example, a gram of algae oil without the fish is vegan algae oil, vegan omega-3s. It sells for about $1.75 a gram. So it's about the same price as a gallon of fuel in some cases. So anyway, something to think about from the algae. We do a lot of work in Yellowstone, so one of the things that we're constantly doing is screening organisms from unique environments for their fuel potential. These are some images. When we stain cells with a Nile red and look at them under fluorescent light, if they light up bright yellow, it's an indication that they're filled with lipids or filled with oil. Some of these organisms are so, there's some diatoms, are so full of lipids, even with a regular light microscope, without even staining, you can see that's basically the color of olive oil. That diatom is full of lipids that can be harvested. We have developed a process where if you add sodium bicarbonate or baking soda at just the right time, we get about a twofold rate of increase in the lipid production rate, and a twofold increase in the extent of lipid accumulation. And so we patented that process, and the company that makes Arm & Hammer baking soda has been paying all of our patent costs. Obviously, they want to sell sodium bicarbonate to all the algae ponds in the country, and paying further development. But again, you can, even with just under regular light microscope, you can see these things are full of oil. We typically get oil concentrations in the 30 to 50% by weight as lipids. So I'm going to switch to another area of research. Again, still a ways off, but we're working on it. We're using organisms from very high temperature environments, and so going down to Yellowstone, getting a small sample from a variety of hot springs, and looking at ways that these organisms can be used for beneficial purposes. And so I'm going to just mention the lignin and cellulose. We're isolating organisms that can grow specifically on things like raw pine chips, wood chips, waste grass, switchgrass, that kind of thing. And these organisms, essentially we just put this material in. The organisms have the enzymes needed to break down the lignin and the cellulose and convert that into useful products. And so essentially we're looking at temperatures in the 60 to 80 degrees C range, very high pH, 9 to 10, so very extreme conditions, what people don't usually think of as conditions amenable to life. But these organisms, they can't live if the temperature's colder than that or the pH is much lower than that. And they've adapted to degrading these compounds when leaves and sticks and whatnot fall into these hot springs. they disappear very quickly because these organisms are so adept at breaking them down. I tell people I have the greatest job in the world. I get to go into Yellowstone, pull samples, and look as an engineer, look for beneficial applications. Again, you look at this hot springs, the light's not great, but you can see just how absolutely clear it is. Any leaf or any stick or branch or anything that's fallen in there completely dissolves in a very short period of time. And then finally, I want to talk about some work that we're doing on fungal transformations of wood. Mostly focus on what's called an endophytic fungus. They live in a symbiotic relationship with trees and plants and whatnot. Basically, they break down cellulose, they break down sugars, lignins, and essentially, just about anything we've given these guys, including municipal waste, newspapers, grass clippings, just about anything, they have the enzymes to break those down and produce compounds that are useful. So for example, it's been termed mycodiesel. Myco means fungus, and producing useful compounds for fuels. And the ones that we're most interested right now, again, with fuel prices so low, limonene and eucalyptol are flavor compounds, which are worth quite a bit more, and you could actually produce these as your primary product and collect this as the secondary product. Picture just showing how quickly these, it's hard to see in this light, but these are just grass clippings straight out of a lawnmower, and the fungus grows just fabulously on those and produces these biodiesel and flavor compounds. Currently, the systems are lab scale, so you can see we're growing them in flasks and up to some solid state reactors. Again, trying to measure rates of production, yields, conversions, those kind of things. But there is, and I don't work for this company, but there is a small company in Bozeman that's starting up that has a novel fungus from Yellowstone and is starting to do these kind of conversions on a commercial basis. They have an SBIR phase 2, and we're in the process of building about a 20,000 liter system over the next couple years to do this fungal conversion into biofuel and higher value products. So that's my last slide. I'll turn it over to Mike unless there's any questions right off the bat.
Any immediate questions right off the bat?
Well, I have one question on the economics of growing up biofuels. Like, in my sense, it still costs 10 or 20 times expensive compared to conventional oil or gases.
Yes, it is.
So do you have any idea how to decrease or what kind of countermeasures will be effective to have this kind?
Sure. So basically, right now, I think the best estimates I've seen, like for algal biodiesel, are about $15 a gallon, $20 a gallon. Again, quite a bit more expensive than petroleum. Again, we're kind of in the early stages, looking for efficiencies, how to maximize productivity. Here's an example. Fungus that produces penicillin, when it was first discovered, made a little tiny bit. Now penicillin strains produce 4,000 times more penicillin than they did when they were first discovered. We're in the first discovery process. Even in the last 2 years, we've made one of our fungal isolates 12 times more productive. So an order of magnitude more productive than it was when we discovered it. We have 2 more orders of magnitude still to work with. And so it's basically why it's a research area. It's not a commercial area yet, but there's, I think there's a future to it. That's not okay.
Great, my name is Mike Wolcott, Washington State University in the Northwest Advanced Renewables Alliance. I want to really give my appreciation to the organizers for this. It's always great to come to Missoula and visit friends and colleagues. It's been great catching up with Brent. We were colleagues a number of years ago back at WSU before Montana stole them. And I apologize to some of my members of NARA, Craig, and Julie's an honorary member because she's worked with us so much, and Nate's on a sister project. If you guys have seen these, you could probably give my talk for me along this line. So I'd like to chat with you today about this Northwest Advanced Renewables Alliance, and we kind of take off where Brent was sort of talking about. These are the efforts he's doing are kind of early stage. We're taking some of these early stage and we're trying to scale them up and put them together in a supply chain to understand sort of what would a fuel supply chain look like within our region. And so it's a nice natural transition for that. I'd like to recognize my co-project director, Ralph Cavalieri, who is the Associate Vice President for Alternative Energy, and for useful work he works with our project. So what we aim at is really to utilize forest residues. So these are the materials that already are harvested, but are not used in any kind of a commercial product. In most cases, these materials are burned on site. And so they're already disposed of and they already release their carbon. We're trying to take that material and put it into an industrial feedstock, a feedstock that could be controlled and utilized in industrial systems like pulp mills are now, convert some of these types of systems to fuels and chemical productions to augment their existing physical areas. And our fuels are actually aimed at aviation biofuels. Aviation biofuels is one area that actually has a lot of support from the consumer side, principally because we're not going to fly planes on anything but liquid fuels in the near future. The energy density that are required for flight and the specificity of jet engines really means that we have to be on jet fuel for a long time. We're actually making jet fuel. We're just doing it from a different source. So we're not making a substitute fuel like ethanol is. We're making the same hydrocarbons, doing it from an alternative route. In conjunction with this sort of process development, the supply chain development, we're really looking at the sustainability of this. And our sustainability assessments sort of really bridge the three areas or three legs of sustainability from environmental, economic, and social aspects for that. And as part of that, we've had sort of large stakeholder outreach and involvement areas. That's where I've gotten to know Julie and my friends here in Montana for this area. To give you just kind of an idea of what our system looks like, we take forest residuals. Those forest residuals are prepared to look something more like an industrial feedstock. That industrial feedstock then is brought into the first stage, and it's called a pretreatment. It's a method that's used to develop, to improve the ability for that wood material to be degraded with enzymes. So if we look at just sort of wood in a natural environment, it will decay over time. It decays mostly from exposure to fungi, which we heard about earlier. Those fungi produce enzymes, and those enzymes break down the various components of the wood as food for that organism. So this is very much that same process. The pretreatment, what it does is it allows this to occur, the saccharification or the release of the sugars to occur in a matter of 1 or 2 days as opposed to years. So we're accelerating that process by modifying that material. It's actually, I took a little bit of time to explain this because it's actually the key step in utilization of cellulosics, is really accelerating that. Once you do that, then you can isolate enzymes, which is, again, part of the work that Brent is attempting to do or is moving towards, is being able to use these different organisms, identify the enzymes, and then be able to produce them and harvest those then for industrial application. So we take ones that have been developed already, we expose the pretreated material to the enzymes. In a matter of 24 hours, it goes from looking like this to looking like that. And that's a sugar solution with a number of other non-carbohydrate components that are dissolved in there, either in a colloidal or a solubilized state. Those sugars then are fermented with a yeast, just like in the breweries that exist around here in Missoula. and we then distill off the alcohol. Instead of producing ethanol, though, we produce butanol, which is a 4-carbon alcohol. Ethanol is a 2-carbon alcohol. This butanol already exists. The pathway to produce that exists in yeast. It's just enhanced in the yeast that we utilize. We work with a company called Gevo, who is a leader in this technology in this area. The reason we go to butanol is when we go to jet fuel, we have to have carbons, hydrocarbons on the order of 12 to 16 in chain length. So if we start with 2, then you got to build up a lot more. In addition to building up a lot more, there's the energy required to do that oligomerization. You start to get different structures and branches, so your yield goes way down. And in the form of isobutanol that we use, it can have a very high yield towards jet fuel or other hydrocarbons along that line. It's also very amenable to other chemical production with that. So that's the primary reason to use butanol. Once we have that butanol, then it's catalytically converted into these hydrocarbons, which can be flown in a plane. This is currently undergoing ASTM standard acceptance, so there's been numerous flight tests that have been ongoing for the last about 4 years in terms of their efforts. Aviation fuels are highly regulated. They're regulated by ASTM, the American Standards of Testing of Materials. That organization, a consensus body, will be voting on this. We expect this spring or early summer ASTM session on that to be accepted as a route towards fuel. It would then be blended with petroleum fuel, just like we get 10% ethanol in sort of a 50-50 blend. So our team is focused up in the Pacific Northwest here, which is our region, but you can see that we have a host of other partners around the country where we bring in expertise that's needed. We have a number of companies, government laboratories, as well as universities and NGOs that are members of this. This is about half of our team at our last meeting, so it's a great big tent project with a lot of really talented people and a diverse group associated with that. Craig, are you in this photo?
Yes.
Okay. I can't find you, so. All right, great. So I just want to talk to you today a little bit. I want you to bring home 2 points, okay? And those 2 points is, we want to talk a little bit about this overview of sort of conversion and economics. We put together big picture models of what this would look like. And really what I want you to walk home with is sort of the idea of the importance of value chain. Again, Brent was a perfect sort of setup because he talked about these high value products that come out and, oh, by the way, we can do fuel. And that's really what we want to talk about here is some of our economic models that show, look, if you want to do fuels at cost, you've got to do other products. And so that's one piece I want you to come home with. The second one is I want you to think about supply chain developments. This is not a plant in a location, but rather it is a chain of companies that have relationships to one another all the way back to the forest. And that if we're going to do that, we have to connect it then to the end consumers along those lines. For that, we've done a fair bit of work here in Montana. So since we're in Montana, this is the Asia-Montana Energy Summit, I thought that I would use Montana focus in terms of some of those. One of those pieces is to look at the opportunities around retrofit and reutilization of existing facilities. You know, this is at the core of sustainable design. Reutilize what we already have, rather than tear it down like we did in Frenchtown and start back over again. So how might we sort of reutilize these facilities that are existing? They already have biomass supplies coming into them. They have a community that supplies a workforce and a relationship on an economic basis. So how do we sort of springboard off those opportunities moving forward in biofuels? So I don't expect you to deal much with this. I just want to show you that our models are based upon very technical sort of mathematical models for these systems to understand how the material flows, what are all the outputs and inputs, what are the costs of these materials, what are the yields that come out, what's the capital expenditures that are required for those. And when we do this, if we did a facility that only did biojet, that took everything in there and we pushed it into jet, we'd probably be at 2 to 3 times the cost of petroleum jet fuel. Okay, that's sort of how we think about many times biofuels. Is let's produce a plant that does biofuels. That's not how petroleum does it. Petroleum takes in crude, They take about a third of their barrel, they put them in a high-value products. They take about 2/3 of their barrel, and they put it into fuel products. The majority goes into fuel. The minority of the revenues come out of fuel. So fuel is actually a low-value product. It's no great shake to get into fuels. That's not a good business opportunity. And it's regulated, and it's subject to enormous crashes in crude oil and things like that, volatility in prices. We don't really need to be in fuels, but we do need fuels for a certain piece of it, and I hope to articulate that. So I just want to show you this one graph that looks at potential revenues when we get away from sort of looking at what the cost of biofuel would be, instead sort of model an integrated process that might produce co-products in addition to that. So typically right now, in most of the plants that are being designed, they're going to burn their non-fermentable materials, like say cellulosic ethanol, they're going to burn that to get carbon credits essentially and help their LCA. So we're looking at that and say, well, that's valuable material. We don't want to burn that. We want to turn it into usable products. And instead, we're just going to get more hog fuel and burn that and help our LCA along this line. So our model doesn't do that. Our model our model does that approach where we utilize everything that comes into this for a product coming out. So this is just one example where we have sort of two lignin. Lignin is the compound that's non-fermentable, so we turn that just into two products, a simple sort of approach to that. We have a byproduct that comes off from biojet, so we try to maximize our alcohol production into jet, conversion into jet. We still remain with one byproduct that comes out of there. And then these are RINs, are sort of the renewable fuel standards. You could think of them as subsidies, but they're not. They're sort of leveling prices to meet the RFS targets on it. So that's what these are right here. So when you look at this, what you see is the majority of the revenues for the facility come off co-products. They don't come off the fuel. The fuel is an economic minority to the thing. So why even do fuels? Well, you need big volumes. You need big volumes to drive scales, because all of these systems scale very, very well. Our cost of production goes down as the scale of facility goes up. And so we need fuels to drive those large volumes, but the revenues are really made from the products that come out of this.
Mike,
So,
can you just quickly just say what RIN is, R-I-N?
I'm sorry. So RIN stands for Renewable Identification Number. That's really exciting, and it helps, right? So what it is this. Okay, so Craig is an ethanol producer. I'm going to talk about with ethanol because it's the easiest thing right now. So we set up the renewable fuel standard. We mean the federal government set up the renewable fuel standards. There's targets for substitution in the petroleum fuels. And blenders, those people who blend your gasoline or other fuels, have to meet that target, okay? If they don't meet that target, they got to pay the EPA money, okay? So instead of doing this sort of in taxes or different things like that, they actually set up a market-based system, right? We're a capitalist country. That's what we're supposed to have, is market-based substitution systems. Of course, the petroleum industry doesn't like our market solution, but that's another story. So Craig is an ethanol producer. So every time he makes a barrel or a lot of that, it gets assigned a RIN. Okay, that's a renewable identification number. So he keeps track of all his RINs. And then Nate is a blender, and Nate is obligated by the federal government to blend in a certain amount of it. So right now it's 10%, right? 10 years ago we hardly saw any 10% ethanol. Now it's in every pump. Okay, that's because Nate's obligated to do that. So Nate has to buy ethanol, but he also has to meet these renewable standards. So he buys the RIN in addition to the ethanol. So what happens is that if there's enough to meet it, well, the RIN value goes to nothing, because there's a market. It's now a market-based system within there. When there now is a very minority of the renewable fuels in there, because it costs a lot of money to put forward, a lot of capital to put it in there, so it's a burgeoning industry. Now there's a shortage of it, the RIN value is very high. So that means that Craig, to put in his new plant, can take the RINs and reinvest that in capital and produce more. And as we start to meet our sort of obligated values, then the RIN value will naturally decline with the market associated with it. So that's what RIN is. So.
Good question, Julie.
Sorry, it's a big answer. It's a complicated system, and it's a mess right now. It's actually very effective, but it's a mess right now. So it's a mess because of lawsuits by the API, American Petroleum Institute, for the petroleum industry, and then weakening from EPA, and so on and so forth. So it's just, but it actually is a very effective system when it's running well. So what do we do? Look at, right, your business, you don't want to deal with RINs and all that kind of thing. So what are these other value chains? Value chains really have to, I just put this up there to say, we have to look at opportunities for other products and for revenue streams and for products and intermediate products all the way through the system. So we have to look at what are alternate products for the biomass, what are alternate products for the feedstock coming into other types of energy products where those might be higher value. What are the sugars that come out of here? What can those go into, and what higher value can we reap from those? In the biochem side, rather than biofuels, can we produce C4s and C8s, which have a very good market right now because we've moved a lot of our chemical refining over to natural gas. In natural gas, you don't get a lot of C4s or C8s out of it, and we're producing butanol, which is a C4, so it's perfect for conversion into other chemical products that are C4s. And then what are other types of fuel blend stocks that come out of this? So how can you maximize the profit of everything coming out of here so that we're not just looking at 2 lignin products, but rather looking at a whole suite of products to maximize profitability? So that's sort of an aspect of sort of building value chains within the system. The other thing I want to talk about is these retrofit of existing systems. And so I just pulled out one chunk that was in that great big complicated chart, and this is pre-treatment. I just pulled this out as an example for that, okay? So what happens is this is just one box, but this isn't actually a process, this is, or a unit operation, this is actually a department. It's one large facility, this one little box is. And this box, consists of boilers and production of calcium carbonate and pressurized refining systems and so on and so forth. Well, if I go over to the old Frenchtown mill, it had a lot of those activities in it. In addition to that, I got another box called utilities that services that from a power generation standpoint, services that facility from a wastewater treatment basis. And I had a lot of that over in Frenchtown also. So how can we reutilize or retrofit these kinds of facilities so that our capital cost to get into this is much lower? Okay? And take advantage of really just sort of basic sustainable design principles to assist this system. So what we've been looking at is developing a site suitable criteria for that. So a lot of these pictures are taken over in Montana here in this area. And instead of looking at sort of greenfield development of plopping it down on a brand new area and doing full development and brand new equipment and all of that, how can we take existing of gray fields that are sort of existing sites that have equipment and facilities on there, or even brown fields that have gone past the other side of the coin? And why do we want to do this? Because they have a site. That site's already developed. It may already have permitting involved in that. It's ideally located because all the ones that weren't ideally located have gone out of business already, so there's self-selection that occurs within there. Many times it already has equipment that exists on the site, and we can reutilize that equipment for this, and the infrastructure that services that, from rails to roads and whatnot. And it has a community. It has a community that thrives and exists because of that facility. This is actually a picture of Bonner. Right? And so Bonner had a community around it. That community now is redeveloping. There's a workforce already component to this. And there's a relationship that extends into cultural and public buildings associated with that. So there's all kinds of good reasons to revitalize our existing communities in this area. The way that we can do that is actually through stakeholder involvement. So we've had these large stakeholder involvements because we don't know what exists over here in Montana. The people who live here and the people who work here and own businesses here and work for NGOs, they're the ones that understand the real opportunity. This is actually a stakeholder meeting that was at the Rocky Mountain Elk Foundation building right outside of town along that line. So we look at this from a standpoint of doing siting analysis for potential biomass depot locations in terms of pre-processing of facilities, inventory to the assets on existing sites, do site design of how that has to be retooled to be able to go forward to this and develop biomass supplies, understand the community impact analysis. I got some numbers for our Western Montana corridor analysis for that. and then scenarios for life cycle analysis. So we use this sort of setup of these supply chains to do all of these, and we actually integrate these outreach teams that work with regional stakeholders and actually some of our education teams to do that. So I want to give you kind of a picture of the Pacific Northwest here. This is all the sort of fuel consumptions for aviation fuel in the area, and the circles are scaled by the size of the consumption. When you look at that, what you really see is there's three sort of demand centers for this. And the three demand centers are the Puget Sound, which is the 900-pound gorilla, the combined sort of Portland market that combines commercial and military aviation there, and then the combined Spokane market, which again is sort of commercial and military aviation along that line. So those are the big centers for that. The petroleum industry has already sort of geared to supply those. So if we look at how petroleum is produced on the west side of the Cascades, we have facilities up around the Canadian border that are refiners. You see them way at the very top. And then that material, the refined products, flow down a pipeline that ends in Eugene. And there's also shipping around or barging around that same sort of pathway to supply those two big markets of sort of SeaTac and Portland. And so in the west side, what we see is the terminus of two sets of pipelines that supply, and they terminate, you know, in or near sort of Spokane to sort of feed those markets. One comes out of the Salt Lake City area, which doesn't have a lot of biomass. The other comes out of Billings refineries. Okay, so the opportunity that we saw was that Western Montana has both an infrastructure for fuels, supplying these major markets, and it has an abundance of biomass, and so this is an opportunity to sort of develop in this area. So Brent asked me to show the billion-ton map, so I'm showing it, Brent. This is just to indicate that basically, you know, the U.S. DOE is looking nationwide at where all biomass is available associated with that, and we can see that, you know, there's a big sort of area in the arid, you know, middle part of the country or western middle part of the country that doesn't have a lot, but in the Pacific Northwest it picks up quite a bit. We're interested in more regional supplies for that, and so when we looked at things, we actually found two locations that would probably be suitable for a biorefinery. One was in Libby, one was in Frenchtown, to readapt those sites. But then to understand how would we supply enough biomass into this and what would we do to maximize, we actually took a more depot approach to this because the density is lower over here compared to the west side. The only way to get it in is to actually look at depots where we looked at existing sawmills as being naturally selected depots because they already are where the wood material is being harvested and so where the residues exist from that. So could we bring those in, do a processing, and then rail it to these sites? And then from this is $40 a bone dry ton of transportation costs. We estimated we could get just shy of 500,000 bone dry tons. It's a smaller facility than what we'd like to see, but it's something that probably could operate. With that then, in looking at those overall scenarios from that, we put together this sort of picture of the Western Montana corridor in terms of where those harvests would take place, and they're not all in Montana. I named it the Western Montana corridor with Craig, I think, early on, and then I regretted it because all the Idaho and Eastern Washington people said, why is it Montana? You're getting most of your biomass actually from Idaho. But what happens is that we looked at this and then did sort of job analysis from that and community impact analysis. And our results of this sort of aspect is that this would probably have about $110 million economic impact from one of these biorefineries, you know, over 700 new jobs created, and we could meet a 60% reduction, which is the target in sort of greenhouse gas production of the jet fuel that came out of that. So this is an example of sort of the downstream benefits that a place like this can have. I was in the session before this that talked a lot about policy, and this is the kind of winners and losers that exist when you do radical policy changes for energy systems. So the last thing I wanted to talk about here, I think, yeah, it's the last one, okay, is I just wanted to indicate that when you look at these supply chains, it's important to not just look downstream towards these chemical products, but also upstream and what are the other opportunities that exist. In order for us to have residuals, it means we have to have a thriving lumber market. If you're not harvesting trees for lumber, which is the highest value use, then there's no residuals to come around with it. And so we've been doing a lot of work, we meaning a number of the researchers around NARA, outside of NARA proper, have been used the supply chain analyses and whatnot that we've been doing to look at sort of new markets for bringing that lumber into durable building materials that can last over 100 years in urban environments through large building construction. It's something that exists already in Europe, where there's low seismic activity. To get it into the US, we have to overcome some seismic challenges, but that provides a very high value and strong use for that, along with sort of long-term carbon capture of that material rather than shorter-term use of the raw material. And so we've been working these concepts along that idea that really facilitate then the continuation of these timber industry and the utilization of residuals that come out of it. So with that, I'll hand over to the next speaker here, and thank you for your time and attention. I got it. I'm a professional.
So thanks, Julie, for having me here today, and thank you for attending the session. I'm coming at this in my position with the Spatial Informatics group and my affiliation with the Gund Institute for Ecological Economics at the University of Vermont. I am focusing with my work mainly on bioenergy from a forest perspective. A lot of my work is in economics and life cycle analysis. Carbon analytics are part of that as well. I have been involved in the last over 10 years now in bioenergy systems that are placed in Africa, working with, for example, tea companies who need wood to dry their tea, down to residential use, charcoal production, and small-scale home use for just heating and cooking food. But also a lot of my recent work here in the US still focused on forestry in Alaska, trying to figure out how residential homes can be heated with local feedstocks from forests. In California, very active scene right now around bioenergy use. A lot of the carbon accounting comes from there. And with that perspective, I tried to put together now a couple of slides and contribute to the more the global perspective on why we talk about biomass, what role biomass plays in the whole energy portfolio across the globe, also with some perspectives abroad, looking at Asia, although most of my slides will have also references to Africa. So I want to start here again with looking at the global energy portfolio and what's being consumed across the globe. And most of you probably have seen something like this before, and probably not too surprising what the outcome is. We have, when you just look at renewables, something like 20% of that in the global energy portfolio right now. And the big question now to me is, where does that actually come from? If any one of you have a guess, please let me know. What is that renewable energy share? Where does that come from? What renewable energy do we have? What sources? And what's provided here? Anyone want to take a stab?
Wood?
Wood? Hydro? Hydro, wind? So the interesting piece here is that actually the overwhelming, does this work? Here. The overwhelming piece of it comes from biomass.
Traditional biomass.
So, and now you're getting right into the exciting piece. What is that biomass? Where does it come from? So, two big points here. Biomass plays a major part in the global energy portfolio when you just look at renewables. It's dominating all the renewables by far. And what is it? There's traditional biomass use, just using wood to heat your home, to cook your fuel. But there's also a lot of other stuff going into this equation that I just want to talk about in the next couple of slides. So this seems to be not quite a surprise to you, but something that's really driving the whole, I think, Not so much the conversation, although I think it should, but it's driving the global economy and societies to a large extent. So when you look at total energy consumption now by nation, you have, for example, here China that under this graph, and there are always inconsistencies when you look at different data sources, but in this graph, basically it says that renewables provide just 1% of the overall energy portfolio to China. That looks very different when you look at an African country, and this is something that I just picked, Congo, Brazzaville, with a big piece of traditional wood fuels used for heat and cooking. Of course, the percentage, or when you look at overall energy consumption, this is a tiny, tiny piece compared to China. And this is not in relation to each other. I just want to make that point here again. But now the big question is, when you look at these two things, you keep that slide up for a second, who is now the big biomass consumer in the world? Where is all the biomass consumed in the world?
Drax.
What's Drax?
Drax Power out of the UK,
Getting the biomass from?
the United States,
To do what?
to generate electricity.
Electricity. So you're bringing up a very important topic, bunch of things. Electricity production from biomass, international trade, and a big piece of the biomass is actually consumed in the industrialized countries. So you have here 26% of the total biomass for energy purposes being consumed on the globe is in the US. When you would add up all the European countries here, you would exceed that number actually. China, in comparison, doesn't even show up here. Probably somewhere lumped in the rest of the world.
Why
So
is the UK using biomass versus coal?
They consider it to be green, clean, and so replacing their coal that's dirty and with the wood pellet and generating electricity with a green instead of a.
Even at the increased cost?
that's right on. So the major driver here is to reduce overall carbon emissions. And they have developed standards that have to be met by utilities, electricity providers. They have to be below a certain threshold. And that's one of the big conflicts right now. How do you actually account for that? When you have biomass to produce electricity, is that carbon neutral or not? And if it's not, what is it? I guess I'll leave it at that right now. Again, keep in mind, a lot of this biomass, although it plays such a big role for African countries, for example, a lot of this biomass is used in industrialized countries. This is a Sankey diagram for just the US in this case, and it gives you the sources where energy comes from and what it is being used for. And the big pieces here is, first of all, electricity generation, how much is used for electricity, how much is used for residential, in terms of electricity, but also in terms of heat. All this natural gas, for example, here going into residential is heat. Commercial, that's commercial buildings in the first case, industrial use, and transportation use. What I want to point out here is, first of all, with most of what we talk about when we talk about renewables, what comes to your mind first? Think about renewables and electricity. What pops up in your mind? Solar, hydro, what else? Wind. And I think actually hydro is not even coming up very often. It's often solar and wind. And the role that solar plays here, or wind, for electricity production is fairly small. Plus, when you really are interested in increasing renewable energy shares, or just getting a full picture of what renewable energy carriers provide, and you just focus on electricity, you're totally missing a couple of other sectors. So the transportation sector, and then especially the residential, commercial, industrial heat sector, are major consumers of energy. heat uses nearly half of what we use on a global scale for energy. Of what energy we use on a global scale is actually going into the heat sector. And that has major implications actually for biomass now. You see that a lot of this biomass here goes right into the industrial piece. And that, in the end, is heat, provision of heat. Nothing fancy. You take biomass, you burn it, you produce heat for processing or for running all kinds of industrial processes. You don't need crazy technology. It's fairly cost efficient, has been done for many decades. My example in Africa, for example, is always the reason that these tea factories use wood to dry tea, and you need roughly 1 to 2 kilos of wood for each kilo of tea that you produce. The reason that they do this is that they are way out in the rural countryside. It would take a lot of time to ship coal or whatever. It would cost a lot. Wood is around the corner, and they often produce it either in their own fuel wood lots or buy just off the gate. That has all kinds of repercussions then from a sustainability perspective, but it's a local fuel that is cost efficient, and it's for heat. Heat is driving the bioenergy agenda to a very large extent, but no one is talking about it. Even when you think about renewables in general, the heat market is absolutely below the surface, and it has major opportunities for increasing renewable energy share, but also for efficiency improvements. And that's the other piece that I want to point out here. When you think about renewable, or when you think about reducing energy consumption for whatever reason you want to do that, be it environmental concerns, be it that you want to make sure. We had this example, for example, yesterday at the panel discussion in the evenings in the Dennison Theater. Someone brought this up. When you look at Millennium Development Goals, and you want to make sure that non-industrialized countries get the same living standard, to some extent at least, as we have in the industrialized world, what implications does it have for overall energy consumption? And one of the panelists made that point that, first of all, you don't need much additional energy to raise living standards by a lot. But coming from the other perspective, you can also decrease energy consumption by a lot in our industrialized countries while maintaining a very, very high living standard, if not the same. So just a couple of components again of looking at energy consumption in general and provision, but also the biomass in particular. I mentioned this now a couple of times, but when you look at biomass, why do we focus on biomass? Why is biomass providing such a big share of renewables right now? One of the big reasons is actually in this graph, and it's a bit complicated to read, but what it actually says or shows you is what measures you have to, in this case, reduce greenhouse gas emissions, what it costs you, and how big these opportunities are. So when you look at the very left side of this graph, it brings up one example, lighting, switching to incandescent or LED bulbs. The reason that this shows up here is that you don't even have to invest much. Your payback period is less than a year. You get immediate payback. It saves a lot of greenhouse gas emissions. There is basically no investment required. But to upscale that, it's not much. There's a very small piece of total energy, fossil fuel energy emissions that you can save from that. Now, when you move further to the right on this graph, you still, up to this point, you still create savings when you implement these measures. Here, for example, you have efficiency improvements for industries in general. It's a very wide range here, meaning there's a huge scalable potential to reduce greenhouse gas emissions. Now, when you move further to the right, it starts with a cost. You need to pay for that. It's not a savings anymore. But you have a couple of big ticket items here, very wide blocks, meaning again, there's a lot of energy or emissions that you can save. And Biomass shows up right around here. In comparison, some solar or full hybrid cars come in very costly, that's why the bar is high, and it's not very scalable, that's why the bar is very thin. And look again at biomass, how thick that thing is compared to others, and how it compares in costs to other options in the renewable energy sector or greenhouse gas emission reduction sector in general. That's why we talk about biomass. And that brings up now, again, the drugs example. And that's, I think, the second last slide that I want to present today. Biomass used to be a local source. There was a lot of advertisement or support for biomass because it provides a local, the background for local economy and so on. And there's a lot of truth to that. And the reason that Michael works on forest residues is that it's very difficult to get these residues out of the forest. Transport costs play a huge role. So you want to keep it local, or you need to find ways to actually increase energy density and reduce transport costs for this stuff. But there are a lot of examples by now, but this doesn't hold true anymore. Drugs importing massive amounts of pellets from North America, Canada, and the US. Huge conversations on all kinds of political levels. This is a projection actually for 2030. And what it shows is that these red bars are exports, meaning South America will export biomass to that extent. Of course, that's an estimate here, but it's already, if you would look at these numbers for today, the overall picture is saying these export bars would be probably, or the bars itself are lower, but the picture itself is the same. South America exporting. The US actually coming out as a wash because it's importing and exporting a lot. Canada exporting quite a bit. Europe consuming and importing a lot of this biomass. Russia, same, big in exporting. China requires massive imports.
And this is just wood biomass, or this is all kinds
This
of forms of
is
biomass?
global bioenergy demand and trade that contains everything. But the big ticket item in the end are pellets and woody biomass, but also to some extent liquids. And for example here, and that doesn't even show up here. This was a huge debate, or it still is in Europe, imports of palm oil from Southeast Asia. Not even popping up here. So this is the last slide. Today we have there's a lot of conversation around how can we scale up bioenergy, how much can we produce in future. There's just a limited resource and where we can get it from. We need arable land, or we need productive land, and that will immediately compete with other uses: food, feed, fiber. This is the food production today on a global scale, and this is modern bioenergy use today. This is modern bioenergy only, no traditional use for right now. The projections, and this is actually a mix of several projections, but projections for 2050 is an increase, just to bring this again, an increase in food production and a massive increase in bioenergy production on the same, if not decreasing, land resource. What that means for the future and how we want to implement that is another question. But that's basically where I want to leave it. I just had a couple of summary points here. Biomass is the largest share of renewables globally and for many countries. It's a very important section of the energy portfolio for non-industrialized countries, but it comes with a big but. Most biomass is consumed in industrialized countries. Mostly used in the heating sector, with huge efficiency improvements. To switch to renewables, bioenergy technologies are some of the cheapest and most scalable options to switch from fossil fuels. And it's a globally traded entity by now. Expansion, major challenge. That's it.
Thank you, Thomas. So I'd like like to invite all panelists to come up and we can have some questions with them. And just some discussion. So, any questions?
I have a question.
Sit and look relaxed.
A copy of your slides.
Yeah, sure, yeah. I don't know what the setup was, but I'm happy to share this with any of you.
Yeah, or if you want, if you want to give them to me, if all of you wouldn't mind sharing your slides with me or something, I can go ahead
I'd like to have more discussion, so.
Absolutely, yeah.
I have a question. So, and Thomas, you kind of hit this. And across the board, why does it seem like there's a lot of policy incentives for renewables in electricity, renewables in liquid fuels, and where is the heat discussion, and why is that not being had? I don't know if anybody has any thoughts on why.
I can take a first quick stab at it. I think this is a very political agenda, but that's driven by what you can see to a large extent. And the electricity market is just very, very sexy. You see that, you don't see that to the extent, but it's just coming up everywhere. I see this in the US, I see this also in Europe, the same thing. No one talks about where the heat comes from. It's not on the political agenda, and no one is really pushing it. A lot of the non-profits from the environmental side who are interested in the topic stick to electricity and don't push politicians on the heat piece, and that also drives then research grants and that are provided through political decision making, and heat is just falling to the sides. I see that slowly changing in Europe at least, but still, when you look at renewable energy portfolios and requirements you see that in the liquid fuels market, you see that in the electricity market, but you don't see anything like that in the heat market.
I think the other aspect is heat production. Unless you're talking about energy efficiency, requires a switch of natural resource that's utilized. I think a lot of environmental NGOs, which push policy on the renewable side, have a very love-hate relationship with that, because in one hand, they really don't want to see utilization of forest, but they don't want to see utilization of coal either. And so they remain relatively neutral on this topic and just choose not to speak on it. I know we've had that experience in trying to recruit environmental NGOs into our NERA process, and we've had a very difficult time getting active engagement on things, because largely we're doing what they say you should do, and so they just don't. I think they don't want to put their limited efforts in those areas. So I think heat's one of those cases along those lines, and the one place they have been starting to come out is in now sort of power generation with biomass. They've started to get more active in that. The NRDC in the United States, especially in terms of what you utilize. Forest residues, they're fine on, but the large-scale production of that's moved into pulpwood that is there because of oversupply of market and a lack of pulp mills, but it's not considered a residual. And so I think that there's that kind of sort of tension along the way with it. With solar and wind, there's no issues.
And you got one other component in there, is that with heat, you have to have water. So you have to do it on a massive scale.
Right.
So now you've taken another resource and thrown it into the mix. So I think that's why no one wants to talk about it, because solar, wind, they don't require anything. Biomass electricity doesn't require.
Good presentations. I'm fascinated by the complexity of something that appears on the surface to be so simple. But the last I knew, over 50% of our landfills were made out of cellulosic material. It could be burned, could be diverted from landfills where they're stored in an anaerobic environment. That seems like such an easy source because it's next to cities, next to power consumption. Then I contrast that against the potential for cogeneration. If heat is in fact a resource, and it's waste heat in industrialized countries that's so poorly utilized, isn't there more efficiencies than just trying to find ways of using local stored cellulosic materials to burn first and find higher efficiencies for the low heat value in waste heat as a resource in urban areas where it's already produced before we go out and mine the micronutrients in forests. Now, I'm making a broad sweeping generalization because there's places where, there's a huge amount of dead and dying trees, and I don't argue that, but my other concern here is the mining of micronutrients from forests and the scale on which we would be doing it if these things were to ramp up. So that's a complex question, but could you kind of throw some ideas and answers at that?
So I'll go ahead and start this off. So I'll first head up to sort of mining up micronutrients in that case. So I want to give an example of sort of our biomass utilization studies that we've done under economic constraints for that activity, okay? So I want to start off with a little anecdotal piece, okay? First time that I actually went to a biomass harvest site out here was actually on a Weyerhaeuser sort of piece of land, and we went out there. There was a grinder set up and an operator near the grinder, but nothing else was set up, and they apologized that, well, everything was there, but you'll be able to see the grinder and sites and so on and so forth. So we did that, and I look out there, and there's a whole mess of slash piles, and there's biomass everywhere. And so I'm talking to the grinder, and I said, the operator, and I said, so are you going to start up operating as soon as we leave? And he said, start up, we're finished. I said, you're finished? He said, oh, yeah, totally, we're finished. And we're moving out as soon as you leave. And so I started to have a conversation with him. Well, why is that? I mean, there's just material everywhere in here. It's like, oh, because we can't get at that economically. So there were slash piles that were going to be burned after that point. But better yet, I mean, there was tremendous amounts of raw material that was sitting on the forest floor for that. So going back to less anecdotal sort of pieces of information, when we look at our economic models, and our economic models are based upon sort of harvest studies, GIS location and surveys of actual slash piles from different types of harvest because they occur in different places, mapping those with roads, looking at sort of cost of logistics to get that to a road, grinding operations, and then movement to a centralized facility that's sort of set up by our siting studies. When we look at all of that, we probably only take 35% of biomass that exists in the region. And on top of that, we currently have studies. We set up long-term soil productivity studies that have looked at that have looked at everything from literally scraping the duff off the floor to leaving everything in there and a host of treatments in between there. And this follows up another long-term soil productivity site that's been in place now for many years to look at a different type of soil type. Basically, except for certain soil classes, that this would not impact sort of micronutrients along the way. And I think one of the things you have to put in there is economic constraints associated with that. That basically the economics are going to take care of this because of the issues with getting the material out. I'm not saying it shouldn't be something we're concerned about. Absolutely, it should be, because that productivity is what's going to keep this sustainable, and there's no question about that. But I think that economic constraints are going to alleviate many of the concerns that are in that direction. At least that's what our studies show. So that's the first part on that, and then the second part evolves sort of around utilization of urban sources, and I'm spot on with you there. That is an area. In fact, I think in general, Brent and I had a long conversation last night. There are so many waste sources which residuals, forest residuals sort of fit into that we ought to be looking at before new energy crops necessarily. I'm very much in that camp. That's why our project's not an energy crop project. So that is definitely a bias to me. We actually had a strong component of looking at urban waste within our regions from construction and demolition debris, but it was largely sort of degraded by USDA because they don't do urban waste. So it didn't fit within their focus of agency. It doesn't fit anybody's focus except for EPA, and EPA is too busy fighting the API. So what happens is it falls through the cracks of things in terms of urban waste sources, but it is really an important area. I can tell you from the work that we've been doing in our area, actually Pacific Northwest, with the exception of Montana, is very well set up to utilize this. And I say the exception of Montana is actually recycling, infrastructure is fairly low. And it's fairly low here because nobody lives here in comparison to Seattle and Portland. So you don't have sort of the mass that sort of generates that. Certainly Missoula has, the social, sort of contract to do this kind of thing, as well as many communities within Montana. But it just doesn't have the kind of densities that are required for the infrastructure. In contrast, King County around Seattle, around the Portland area, King County set themselves under carbon targets 10 years ago, and part of that was handling solid waste. They have a very well developed sort of solid waste handling system that was actually firing a lot of pulp mills in the area that are starting to close or have closed, and there's an excess of material within there. Paper is sort of a maybe not so great source, and the reason why is that recycling rates of paper are through the roof. Very high rates of recycling of paper. That industry has really responded in that direction. So it's kind of in the papers that do exist are more difficult to handle and so on and so forth. But construction and demolition debris is a great opportunity for this. You're spot on. It's where the people are, where the power of the fuels are required, and if you can integrate that system into there, I think there's a lot of benefits to be had from that. And I think you had one more question embedded in there. It was a big question. is sort of looking at combined heat and power. I think I'll put that to. And most of the new facilities look at that. What's required is to have a thermal host. So what we don't have, which is well developed in Europe, is centralized heating and things along that line that exist in that. Our communities aren't designed like that. Our population, densities are not as great, and oftentimes cases, and where they are as great are urban cores where maybe that's not as an appropriate generation sort of scheme. So actually integrating an industrial heat cases and having an industrial thermal host for the waste heat in that are good opportunities, and that's where you see most of the the new biomass facilities going up is in those sort of combined heat and power areas. So,
well, thanks for the response. But in Africa, the tons, the ton of biomass to dry a ton of tea. Could you talk about the deforestation potential in Africa when maybe there could be other more benign ways of drying tea there?
Yeah, that brings you to. So I have worked on that issue in Uganda and Kenya mainly, and the private companies who operate there are often internationally owned tea production companies, and they are very concerned. They are very well aware of the energy issue, and most of them have their own fuelwood plantations that they have been running. This tea is an old industry. They have been developing this for decades, if not 100 years, and they have it figured out to a very large extent. So providing their biomass from their own fuelwood plantations, mainly eucalyptus. In Uganda or in Kenya, there are also then cooperatives. One state-owned cooperative or state-regulated cooperative that doesn't have that. They work with an outgrower system where they just have the processing facilities where they dry the tea, but they buy the tea from farmers, and they also buy the fuelwood from farmers. They buy every piece of fuelwood that you would deliver to their gate, and that of course has no implications when you think about deforestation. So it's a very mixed picture with the tea industry. You have actually, I think you have great expertise there in managing fuelwood plantations and then designing fuelwood plantations in the tea industry, something that you could expand a lot, but at the same time there are difficult examples as well.
Thank you, Thomas. We're at the tail end of the session. I would imagine if you want to buy one of these guys lunch, I think we're at the lunch hour. Was it 11:45 or?
We are at the lunch hour. There is actually a walking reception in the Fine Arts Building, which is just across the street. It's the same building as the Dennison Theater. There will be people to direct you to it. They'll be wearing these white Ames t-shirts. We hope you join us, and please take your food. You may take it back to the Dennison Theater to join us for our next afternoon panel, The Future of Global Energy.
Thank you.
Thanks.